Okay, thanks for joining the final COSIC seminar of today. This is a talk I'll be giving at RSA conference, Cryptography track next week. And it's titled Masking Gaussian Elimination at Arbitrary Order with application to multivariate and code-based PQC. It's joint work with people at COSIC, Suparna and Ingrid, and colleagues at ISI Kanpur, or Kolkata, and IIT Kanpur. So I have to show this slide. So the outline of today's talk will be, I'll first give a brief introduction to multivariate code-based PQC and show a bit how they're vulnerable against certain types of side channel attacks. I'll dive into the countermeasure that we proposed based on masking to protect against certain types of side channel attacks, DPA attacks, specifically for the Gaussian elimination and back substitution operation. And then finally, I'll talk a bit about the implementation we did of our countermeasure on an embedded device and how we evaluated its performance and its security. So I'll start at the beginning, which is quantum computers. I've put a picture of, I think, the most recent one, which made the news headlines, the latest quantum computer or quantum chip by Microsoft. There's many institutions working on developing a large and scalable, low-noise quantum computer because it promises to bring breakthroughs in several fields, biology, chemistry, economics. But unfortunately, in the field of cryptography, it's also a threat because there exist algorithms which, using a quantum computer, could break public key cryptography. And thus, there is kind of a need to replace these algorithms, public key algorithms, which are currently deployed, with post-quantum variants. So post-quantum cryptography is kind of an encompassing term we use to bundle algorithms which are resistant against classical attacks, which we know and can currently perform, and quantum attacks, which will be able to be performed in the future once a large and scalable quantum computer is built. If you want to learn more about this or get an update on recent developments, there's an excellent keynote talk which was given at the PQ Crypto conference a few months ago, or I think 1 month ago, where the title is Unexpected and Expected Developments in the Field of Quantum Computing, and it gives kind of a nice high-level overview of the recent developments. I would highly recommend if you're interested in this. But for the sake of this talk, we'll kind of assume that at one point there will be one, and thus we need to anticipate this threat, and we need post-quantum crypto. Now, as I mentioned before, public key crypto is used in many places, but one example is in digital signatures. What is a digital signature? It can be used to authenticate the authenticity of a message and the person sending it as a receiver. So I'll quickly illustrate. So we have a message and a private key from the sender. The sender can use this private key to generate a signature, attach this to the message, send this over a channel which might be interfered with, along with its public key, and the verifier can use this public key and the signature and the message to authenticate that the signature was generated using the associated private key, and that it's for that message. So this type of structure, this digital signature, it relies on this public key crypto and thus is vulnerable against quantum attacks. So we need a post-quantum variant for those. And kind of the state of post-quantum digital signature algorithms, I think a main or a big player in this field is NIST, the National Institute of Standards and Technology. They've been, since 2016, doing this post-quantum standardization effort, of which last year the first standards, also for digital signatures, were announced and published, and kind of encouraged everyone in industry and government to start this migration, because it will be a low and slow and very painful process to get there. And they've kind of set a hard deadline, right? By 2030, we want everyone to at least have some sort of hybrid structure using both classical and post-quantum crypto. But the effort is not over. There's still actually an ongoing process in which NIST is looking for additional digital signature algorithms which rely on different hard problems and kind of coming from the mentality that if one of those currently already standardized schemes gets broken in the future, we have some backups available to be like swapped in so that we can still protect against those quantum attacks. And they're looking specifically at algorithms from different kind of hard problems. So on the left, these are the current standards. They're based on lattices and hashes, kind of more established hard problems. And on the right, we have more more niche types of post-quantum, so based on isogenies, based on code-based and multivariate-based crypto, of course. And this process is currently ongoing, and with the hopes of eventually finding or adding a few more standards to the current list. And specifically for multivariate and code-based PQC, one of the critical parts of these schemes, and it's shared among all of the current candidates, is solving a system of linear equations. So I put the general form on here. You have m equations, and you kind of need to find x so that you satisfy for all of the a's and the b's the set of equations. And I will not bore you with going back to the linear algebra courses, but you can take this system of equations and put it in a matrix form and represent it as this. And why do we do this? So we again have m equations with the m rows, m columns, and then we have the extended m+1 column for the b coefficients. And if we put it in this form, we can actually use Gaussian elimination to bring it in a structure where we can directly read out the solution of our system. So it looks kind of like this. This is what we call a row-echelon form, where we have our diagonal being all ones, the elements below our diagonal are 0, and then we can start from the bottom and read out our solution, substitute that in the row above, and kind of build our way up and find all m solutions. And we can do this using 3 operations. So we can swap rows around, we can multiply rows with a constant, and we can add different rows together. So that's the allowed row operations. So I mentioned also that we are working in the context of side channel attacks. So what are side channel attacks? Well, if we have an embedded cryptographic device which is performing some cryptographic operation using some sensitive or secret key material, if an attacker can passively listen in on this device or even actively interfere with the operations, if the execution is dependent on the secret key material, the physical leakages of this device might give you or might help the attacker learn something about the secret key material which is being computed on. So, like in this case, in the scope of this work, we'll consider the passive scenario where an attacker is passively listening on a device, measuring the power consumption, and we want to make sure that there is no correlation between this physical leakage and the secret key material on which we're computing. And a well-established countermeasure against these types of attacks, so differential power attacks, is masking. The only thing we need to know here is that for masking, we kind of split up our sensitive data into multiple shares. We compute on an incomplete set of shares so that an attacker can never recover all the shares of one secret and thus can never learn something useful about the secret. And we do this by adding randomness and kind of reshaping operations to make sure that we guarantee these properties. So if we apply this to the slide I showed before, we get a big matrix in which our secret elements in this matrix are split into, in this case, 2 shares. One important remark here is that the type of sharing or how these shares or how these values are shared and can be recombined is quite essential because different types of sharing are preferred by different operations. What do I mean by this? If we want to do like an XOR, a GF256 addition, we need to have, or this type of operation prefers Boolean sharing because if you have a Boolean share, you can just share-wise kind of XOR shares together, and it's easy, just a share-wise operation. So you scale with the amount of shares you have. Whereas, for example, if you want to multiply 2 shared values, you obviously prefer multiplicative sharing because then you can again do in a share-wise fashion, just multiply share 1 with share 1 of the other variable, and it's easy to do. So different types of operations prefer different types of sharing. So this will pop up later in the presentation. So this is kind of the input we have. We have a big matrix. We need to solve this system of equations. So how do we propose to do this? I'll walk you through it. So step 1, of course, is trying to make the pivot element, or the pivot element, non-zero, because we want to eventually make it 1, remember? So how can we do this check? Well, there exists a gadget called sec non-zero. There actually exist many different variants, but this one was formalized in chess last year. And it allows you to take a masked value and to get a masked value back, which indicates if it's 0 or non-zero. Because we obviously cannot just recombine both chairs and check for the non-zero property. That would leak information about the sensitive value, right? So we can get a Boolean back, kind of a true-false, but in the masked, like in a masked form. And we can actually not unmask it. We cannot leak if it's 0 or not, and I'll show you why. Let's say this pivot element is 0. So we take the sec non-zero, we get the masked Boolean back, we unmask, and we get the case where it is 0. Then we could, for example, swap rows and hope that that other element is non-zero. But this means that we're actually doing operations depending on our secret, and the execution time will also be dependent on how many zeros or non-elements or elements are not 0. So we cannot do this. Like, it's not constant time, and it leaks information. So we propose a gadget to do this in a constant time. And the high-level idea is that if the element is non-zero, we can add just 0 to it because it is non-zero. And if it is 0, we can add other rows to it instead. But in the time domain, there is no difference, right? We're just adding stuff, either 0 or non-zero stuff, to make it non-zero, while never unmasking or doing any operations depending on the unmasked properties of that value. More details are in the paper, but from a high, like if you look at it on the slide, we have that value, and we can just add either 0 or the row below to that value, trying to make it non-zero. And we can repeat that for all of the rows below until we get to the bottom, and then at the end, we get the value which we hope is non-zero. We also looked at the early stop property, so you can kind of compute based on the modulus of the values you're working on and the dimension of your matrix. You can actually compute the probability that that value will be non-zero after a certain amount of rows, and thus kind of put that on some like 2 to the minus 64, and then say, okay, that probability is sufficiently low. We don't have to do the entire matrix, which saves a bit in performance. But yeah, more details are in the paper. But you can do that. You can stop early. You get that value. And now you want to check if this pivot is actually non-zero, right? Because then you can continue to step 2 or step 3, making it 1. And for this, we can actually use the sec non-zero with unmasking. Because if it is non-zero, or if it is 0, still after doing all of these additions, then we kind of cannot find the unique solution for this set of equations, and we have to anyhow restart the signature procedure. So we throw away that data. So leaking anything is just, it doesn't matter. It's data we will not use in the actual signature. So we can leak that. And if it is, if we leak if it is non-zero, then we don't learn anything new, because that means we'll get a valid signature out. So we're not leaking anything here. So we can just unmask, we throw that away if it's 0, and then we get to step 3. So we have a non-zero value, we know this, and now we want to make it into 1, because it's a diagonal element. And to make it 1, the easiest way to do this is to multiply it with its multiplicative inverse. But as I mentioned before, multiplication is nicer to do in the multiplicative domain, but we're working with a Boolean shared domain. Thus, we propose this B to M inverse conversion, in which we take the Boolean shared value and we convert it to its multiplicative inverse. So it's based on this B to M conversion, which was used previously in the context of AES multiplicative masking, but we can use it here. And then we have our sec scalar mult gadget, in which we take the pivot element, which is Boolean masked, and we multiply it with the multiplicative masking of the inverse. So one note is here, we don't convert the original or just the normal pivot element, because that would cost an additional B to M conversion and then an M to B conversion at the end, which is quite costly. But we kind of get a nice trade-off here, because we're working with, only linear operations, because we can just do this for both chairs. while not having additional B to M or M to B conversions. So kind of a nice trade-off between not having to do all of the conversions, just one, but kind of doubling compared to just having both of them in the multiplicative domain. So we kind of balance out the cost and the performance. So if we do that, so we do the B to M conversion, we multiply with its inverse, then we get to a value which unmasks to 1. It's still 2 shares. And then we just have to repeat that for the entire row, of course, doing the same thing. And then the final step is to make the elements below non-zero. And this is actually the most costly step because we need to add a multiple of the first row to the row below to make it 0. I'll not dive into the details here below, but the gadget is called sec_mod_sub. It's in the paper. But it uses the same row operations as above, and you can do that for all of the elements below. And then you kind of start again this whole loop, right? You move one row below, one column to the right, new pivot element, and you repeat the same story. Check if it's non-zero, or try to make it non-zero, check if it's still non-zero, and then go through all of the steps. So you'll end up with something that looks like this, where you have values which unmask to 1 in the diagonal and values which are unmasking to 0. And then you can start doing your back substitution by starting at the final row. One thing we did here is, the details are in the paper, but we do some early unmasking because so once we are in a row and we find that final value, we can just unmask it and we don't need to compute with the masked value anymore because the final value is public anyway, it's part of the signature. So we can just unmask it and use the unmasked value to do the computations. So we save a bit of cost there. So this technique is kind of general in the sense that it can solve any type of system of any dimension, but we then specifically looked at the cost for the round 2 code-based and multivariate-based signature schemes. So the full cost analysis for their parameter sets is in the paper. There's some interesting things going on there where, because mainly the cost is determined by the matrix dimension, so the amount of rows and columns you have, and also slightly by the modulus and of course the amount of shares you have. But yeah, in some cases, one example is that the UOV scheme, for example, I don't remember exactly which 2 schemes, but you can kind of get a nice trade-off between the amount of, like the size of your modulus and also the amount of rows that you have. And some schemes opted to just have a very large M, which like offered them a nicer prime or a nicer Q modulus. But because you have such large M in the masking domain, if you look at the masking operation, actually you get way more costly. So there are schemes for which the masked variant of security level 3 is way cheaper than the masked variant of level 1 of another scheme. So kind of counterintuitive. And just to give some numbers, so we implemented this on an embedded device, the ARM Cortex M4. And I think the main number that stands out here is that we're looking at a 15x overhead for first order. This goes up to 38 times, 39 times second order, and then even up to 100x if we're looking at third order. And the main cost here is coming from this step 4, as I said before, because you have to do a bunch of multiplications and additions in the masked domain for each of the columns below. So it's quite expensive. These numbers include the on-the-fly randomness. We need a lot of it, but yeah, that's kind of what it is. And then this is kind of ongoing, and this is not included in the paper, but something I want to show here is that we actually took the countermeasure and put it on the device and did some DVLA measurements. So we tried to see if there's actually still a secret dependency on the power trace of this device while it's doing the operation. So on the top here, you can see what such a power trace looks like of one full Gaussian elimination. And then if you just do the operation without the masking, without the countermeasure, you get something like this. And so the higher the peaks, the more leakage or the more dependence and correlation between the secret and the power measurement. And then when we activate our countermeasure, you can see that we can stay within these red lines that we do, which is kind of the threshold to kind of ensure that the leakage is non-significant. And so the countermeasure works. That's kind of the conclusion. And for this, we have to do a bunch more than just the countermeasure, but also mitigate bunch of micro-architectural effects which are happening in the pipeline, in the register file, in a bunch of places. So the key takeaway, how to apply our results, because we're at CT RSA, or will be next week after all. So I think it's critical to when looking at PQC to also consider the real world scenario where these algorithms will actually be deployed at some point, including in embedded device. So there is a need for both security and efficiency. And this kind of comes into play both during the design phase of the scheme, which is currently still ongoing, but also the implementation of these schemes, which will be something like in the coming years to look at. And yeah, like, as I said before, this PQC transition, it's ongoing, or it should be at least. So yeah, also, as I mentioned before, there's many standards. There will be many standards, which is kind of a unique situation. So yeah, this brings its own challenges in the agility frame, because like, with many standards, they need to be interoperable and like, yeah, all bunch of messy stuff. So this is definitely something to look out for in the next few years. So thanks for your attention, and happy to answer any questions. I don't know, time.